Hello everyone and welcome to AB Calculus. This is section 1.1, day number 1, a review of functions. Our objectives for this lesson are to talk functions in the form of equations, tables, and graphs, talk about domain and range, as well as some composite functions and its notation. So the textbook definition of a function is a rule that assigns to each x in a set D a unique value denoted f of x. The set D is called the domain of the function, the range of the set of all values of f of x produced as x varies over the domain. Here's a simpler definition. Okay, so basically a function is a set of points that is produced by some inputs, which we would call the domain. Ooh, I chose yellow, great. Which are the x values or the independent variable. And the outputs of our function are the y values or the range, typically denoted as y. Now some functions might have a domain or a range which is bounded, has boundary points. So a function whose, let's say, domain has a closed interval from 1 to 3 has boundary points 1 and 3. Other functions might have an open interval denoted with the parenthesis, let's say from negative infinity up to, but not including 0. Now, a domain or a range could have a closed end and an open end. For example, let's say the domain of f of x is from 0 up to infinity. So that would include 0 and then have no upper bound. Okay, so let's get into some specifics with regards to the domain of a couple of functions, as well as its range. Now, in example 1, we're looking at the function f of x equals 1 over x. So this first function here has a limitation on its domain. And the first limitation that we talk about is that the denominator can never equal 0. If it does, that's a discontinuity in the function, which means it's a limitation on its domain. So the domain of f of x, which is 1 over x, is everything except for 0. So negative infinity up to 0, and 0 up to infinity. As I look at the function 1 over x, what number would make x equal 0 or the denominator equal 0? That would be x equals 0. Therefore, another way that we could write this domain of f of x is x cannot equal 0. Okay, just another way that we could write that. Now the range of f of x, I'm going to think about more in a visual sense. Here's the xy axis, the graph of 1 over x. This isn't very good, but I'm doing my best here. It has a vertical asymptote at x equals 0, hence the limitation on the domain. And it has a y-intercept at y equals 0. Therefore, the range is going to be the exact same interval as the domain. Or we could say that y cannot equal 0. Okay, so our first limitation on the domain is that the denominator cannot equal 0. Let's look at the second limitation on the domain. As you may already know, you can't take an even root of a negative number. Therefore, in the situation of f of x equals the square root of 4 minus x squared, so we desire 4 minus x squared to always be greater than or equal to 0. Therefore, if I solve this, x squared will be less than or equal to 4, which means that x will be between negative 2 and 2. That tells us the domain of f of x would be on the interval, closed interval from negative 2 to 2. Now, the range, again, like I did in the first example, I'm going to consider in a visual nature. But in order to do that, I'm going to set y equal to the square root of 4 minus x squared and help you to kind of work through visualizing this in a formulaic sense. Okay, so I'm going to square both sides. And then I'm going to add x squared. Now, you may recognize this. This is, if I put it in this form, this is the equation of a circle centered at 0, 0 with a radius of 2. Now, what you'll notice is that I don't have a plus minus here on the original equation. All I have is a plus. Therefore, this is representing only one half of that circle. So that circle has a radius of 2. Therefore, its range is inclusive from 0 to 2. Okay, so what are the conditions that limit domain? Well, the denominator cannot equal 0. That was a weird cue. Cannot equal 0. And the expression inside a radical, an even radical, which is called the radicand, has to be greater than or equal to 0. So the radicand of an even root has to be greater than or equal to 0. Okay, let's look at a little function notation here in example 3. Here I have f of x, which is negative 3x squared. Function notation for an input, right, an x value of negative 6. If I want f of negative 6, I'm going to evaluate by plugging in a negative 6 into my function. Therefore, I'd have negative 3 times 36. Thus, f of negative 6 is equal to negative 108. Okay, how about f of a plus 8? Let's consider a an integer, or some, and I guess it doesn't have to be an integer, but it could be a real number. F of a plus 8 would be negative 3. A plus 8 quantity squared. That would be negative 3 times a squared plus 16a plus 64. Thus, f of a plus 8 would equal negative 3a squared minus 48a minus 180, 192. There you have it. Okay, let's continue on with a little bit of function work. All right, let's continue here with the textbook definition of a composition of functions, or composite functions. Given two functions, f and g, the composite function, this is the notation f of g of x, is defined by f of g of x, which is, this is probably a more familiar notation for a composition of functions. It is g inputted into f of x. It is evaluated in two steps. Y equals f of u, where u is equal to g of x. The domain of f of g of x consists of all x values in the domain and g such that u equals g of x is the domain of g. So let's find the formula for f of g of x if g of x is x squared and f of x is x minus 7. So f of g of x would be f of x, which is x minus 7 with g of x inserted into that as the independent variable. Therefore, f of g of x is x squared minus 7. Now f of g of 2 is equal to f of g of 2. Well, g of 2 is 2 squared, and 2 squared is 4, and 4 minus 7 is negative 3. Therefore, f of g of 2 is negative 3. So using formulas, we can work with that in the function notation. Let's look at a graph. So let's use the graph below to find f of g of negative 4. So the first thing that I want to do is I want to find g of negative 4. Well, g of negative 4, it's going to be in red. G of negative 4 appears to be negative 4. Okay, so if g of negative 4 equals negative 4, then f of g of negative 4 is equal to f of negative 4. And f of negative 4, over here, input negative 4, is positive 4. So f of g of negative 4 is equal to positive 4. All right, let's look at the same concept now using a table. All right, so we want to use the table below to find g of f of g of 4. So I'm going to work my way inside out. First, I'm going to find g of 4. Looks like g of 4 is 3. Now I want to find f of g of 4, which is going to be equivalent to f of 3. And f of 3 is 2. Now I want to find g of f of g of 4, which is going to be equivalent to g of f of 3, which is the same as g of 2. And g of 2 appears to be 2. Therefore, g of f of g of 4, do I have enough parentheses? No, one more, is 2. All right, everyone, that's it for 1.1 day number 1. See you in the next video.